No, 579. Yeah.
I have one.
Oh, you guys, I'm sorry. I'm trying to be short and sweet to the point. Alright, here we go. Number 14. It's arithmetic. And D equals -3 because it's decreasing. Don't say subtracting 3, say -3. Number 40. You guys can check out the first 5 terms. 200, 190, 180, 170, 160. Number 48, 70. Number 54. You can see them, the first, the 50th term, and then the 50th sum. To find the 50th sum, you have to plug in n over 2. You have to plug in the first term, -6. You have to plug in the last term, so you have to find it using the formula, which is 190. Solve, 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 4,600. You guys got it? Still kind of up there. Number 66 is D as in delta, and number 68 is A as in alpha. Beta, gamma, delta, epsilon. Beta, zeta. And is that it? Oh no, number 84. Woo! 84 was a beast. The first month, they paid $250 plus an interest payment, which ended up being $300 total. So if you guys were noticing, they were asking for a couple different things. They wanted to figure out what was the unpaid balance. So they paid off $250. They had this much left, but they're paying this extra amount of interest. Hence why you don't want to go into debt as much as is possible. Because you're paying off your loan, but you're also paying this extra stuff. And this is just something small. Was this a car? What was this? A parent loan? A loan to parents, a loan for college. That couldn't be college, not these days. Anyway, maybe a very, very, very used car. Anyway, so, actually it's still 5,000. That could be a nice used car. Coming back, $250. $250 went towards the balance, but then they also had to pay this interest. So then every month, since the balance got a little bit less, whenever they paid off the $250, they were paying less interest, and so it got smaller and smaller and smaller and smaller and smaller. After 12 months, they were paying, or they paid $272.50 for that month, but they had paid off a good amount of the loan. For letter B, you were supposed to figure out, I think, the total interest that they ended up paying. So the sum of all the interest, the crazy thing was, the first month, which would have been the first term, they paid $300. The very last month, I think, for when they paid off the entire thing, oh no, the 20th, that's what you're looking for. The amount they pay in the 20th month would have been $252.50. So if you find the sum of all the money that they paid, it would have been $5,525. $5,000 was towards the unpaid balance. So they did it kind of in a unique way you guys might not have thought of doing. They just figured out the total that this person paid over the entire life of the loan. And they said, okay, how much extra did it end up being that was interest? $525 was the answer. $525 was the answer. And that was a 1% loan. House loans these days go to 3.5, 4, 4.5%. And if you think houses are really cheap house might be like $300,000. Whew, that's a lot of interest over the life of the loan. Hence why you want a good down payment. All right, cool kids. Is there anything? Sorry, personal finance. I'll stop. In section 9.2, we need to go over. For 9.1, the little review problems. Oh, there's bugs in here because I think there's cookies. Actually, I think it's from the recycle thing right outside the door. It kind of smells out there. I don't know what's going on.
Maybe on the left.
Yeah, it's like the recycle one though. I can't find them. Alright, we're good then. Section 9.3, let's try to bust it through. All that's new is a different type of special sequence called geometric.
So will this be tomorrow, or?
We're going to try it for tomorrow. We'll see how it goes. It would be very, very, very beneficial for our honors pre-calculus help if we were able to do that. It's going to be super similar to arithmetic until the very end. It's going to be super similar to arithmetic until the very end. Meaning, we're going to talk about how to find nth terms. We're going to talk about what the pattern is and how to find formulas. So we don't have to jumpity jump all the time. Formulas for the nth term and formulas for the nth partial sum. So we're not really covering tons of new vocab except, what's the pattern now? Are we adding? No, but it's kind of hard to tell what we are doing. For arithmetic, we were adding the same constant over and over, and we could tell because we could use subtraction to figure out what that constant was. Geometric, now we're doing something every time by the exact same number, except we have to use division to figure out what it was. So what do you guys think the pattern is? Yeah, multiplication. If subtraction helped us find the adding pattern, division will help us find the multiplication pattern. So we're going to be multiplying by R, which stands for the common ratio. We can say the common ratio is the constant multiplied to get from one term to the next. In a geoseries. That's what makes a little more sense to us when we're talking about multiplying by the same constant over and over and over again. But how do you figure out what was multiplied? You divide. How do you figure out what was multiplied? You divide. So common difference for an arithmetic, common ratio for a geometric. You think arithmetic is the easier math? And the easier math is going to have the easier operation, so you're adding by the same thing every time. We can also think the term will be easier. A difference is easier than a ratio. A difference is just subtraction. A ratio is division. I don't know, just silly ways of remembering stuff. Ways of remembering stuff. You guys almost have it? You're done early. Pre-cal took a test today, so homework 7, 1, 2, 3, 4, 5, 30. I didn't collect from seniors and not collecting from pre-cals. Since a few of you guys are still writing notes, can I give you an illustration of a geometric series? What's the difference between a series and a sequence? Sequence is separated by, series is separated by. What's a series? Sequence is commas. Series is addition. Series, remember, it has this big old sigma and you're adding things together. Okay, let's give this some arbitrary length. So we'll say 1 arbitrary unit. Okay, 1 arbitrary unit from me to the stool. Cool? We're going to try and think about measuring the total distance I'm going to travel. However, there is a set parameter as to how I'm going to travel. You ready? Every time I take a step, I am going to, as best as I can approximate, we're thinking about this more theoretically, but I'm just illustrating the idea. I'm going to cover half the distance from me to the school. So every time I take a step, I'm going to cover half the distance from me to the stool. All right? So this is 1 arbitrary unit. So we'll just call this 1 something. Bigger than a yard, less than a mile. I just jumped there. What's bigger than a yard and less than a mile? What's another unit? Meter? Still,
it'd probably be like 2
yeah.
meter. Maybe even more than that.
Anyway. So, question. if I'm supposed to cover half the distance from me to the stool, how far have I traveled? Half an arbitrary unit, so I've traveled 1/2. Okay, now, I'm going to travel another half of that. So I've done 1/2, and now what did I travel? A half of a half, so a fourth. Okay, so 1/2 plus 1/4. I'm going to do half of that. There's 1/4 left. I did 1/2 of that, which is 1/8. So 1/2 plus 1/4 plus 1/8, right? Okay, cool. Now what am I doing? 1/16. Now what am I doing? Now what am I doing? Now, realistically speaking, am I going to reach the stool? Am I going to get to where I can't, like, literally cut it anymore and I'm basically like, hey, I can sit down, I'm there, right? But mathematically speaking, how can we show that series? I traveled 1/2 and then, how long would it take me to reach the stool? It's called Zeno's paradox. It's a famous one. And some people say Zenon's paradox. Either way. The paradox is, will I ever reach the stool? And the theoretical answer is no. However, in the real world, is there a point where a number becomes arbitrary in the sense of realistic measure? Kind of yes, kind of no. In the sense of like measurement from me to the stool, yeah, it's going to become arbitrary. But if it talks about like the percentage probability of something failing in an aircraft, and you have all these different components, and you take all the different percentages together, that could be dangerous. That's probability. So little numbers can have big meanings. But coming back here, question: what kind of series is this? It's geometric because every single time we are multiplying by what? Times 1/2, times 1/2, times 1/2, times 1/2. True? Okay. So question, if I'm adding an infinite number of things together, what's the sum going to be? Infinite. Bigger and bigger and bigger and bigger. You're adding and adding and adding and adding. However, hold on. Where did I start from? 1. And if I keep adding and adding and adding and adding and adding and adding and adding, am I going to go an infinite distance to the stool? No. I'm going to get closer and closer and closer and closer, and the mathematical term for getting closer and closer and closer and closer to a finite number is what? Approaching. We can make it even snazzier. We can say converging. Not diverging. Divergent, what? That's actually a math term? Anyway, convergent. I'm going to converge to the distance between me and the stool, which is what? So what does this infinite sum equal? We need to figure out mathematically how we can show that to be true. What? Anyway, coming on back. We're not quite to geometric series, though. We're still at geometric sequences. By now, everybody had to have written that down, right? Let's go play with sequences for a bit. We're trying to figure out how we can show mathematically an infinite sum is a finite number. But first of all, oops, undo. Some of you might be thinking that 3 is 1/3. It's a very similar idea. Okay, sequence. Hold on. Sequence. How can I find the 10th term if I have the first, second, third, fourth, fifth? Yeah, I can follow the pattern of the sequence. So I can go ahead and look at the sequence itself and say, okay, finding, oops, maybe you guys need to see that. Finding the nth term. I have the first, I have the second, the third, the fourth, and the fifth. We could go jumpity jump, jump, jump with the pattern and question, as you're writing, what is the pattern? R is equal to 2. This is geometric. I am multiplying by a constant every time. So I can say that R is equal to 2. So to get from the 5th to the 10th, how many times 2's would I have to do? Yeah, from the 5th to the 10th. That'd be the 6th. 5th to the 6th would be 1. 5th to the 6th to the 7th would be 2. 5th to the 6th to the 7th to the 8th would be 3. To the 9th would be 4. To the 10th would be 5. To the 6th one, 7th 2, 8th 3, 9th 4, 10th 5. Huh. Well, how could I do that maybe from the beginning? I could do times 2, times 2, times 2, times 2. Times 2, times 2, times 2, times 2, times 2. There we go. Could multiply times 2 quite a few times. 5 times to be exact. Or, how many times can I multiply by 2 from the first term? 9 times. Remember the whole like addition, how we could plus, 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 plus so many times? This time it's going to be times, times, times so many times. So I could say a sub 10 is equal to a sub 1 times 2 times 2 times 2 times 2. How many times? 9 times. But question, kiddos, how do we show repeated multiplication in a snazzy grown-up math way? Yeah, exponents, right? Like squared, cubed to the 4th power, 5th power. So using exponents, can't I say a sub 10 is equal to, what's a sub 1 again? Times 2 to the power of 9. So is that 6 to the power of 9?
No.
No, PEMDAS says you don't do 3 times 2 first. What do you do first? Exponents. 2 to the power of 9 first. 2 to the power of 9 is going to be 2 cubed times 2 cubed times 2 cubed. Well, that would work. So that'd be 8 and 8 is 64, and 64 and 8. Then we need that times 3. So 2 and 3 and 512 and 512 times 3 would be 1536. Actually, I'm just spitballing there. I might have done some bad math.
64 times
64 times 8?
I got the 2 times.
Huh. Okay, so final answer? Oh, 1536 was right?
Yeah.
Oh, okay. I thought you guys were saying I was wrong. Sorry. 2 to the power of 9, yeah, is 512. 512 times 6.
You wrote it.
Thanks.
That's dangerous.
Go team. It is dangerous though. So do you guys kind of see where the formula comes from? Geometric, you're multiplying multiple times, multiplying. We can show with the power, but the power or the exponent is going to be, or going to need to be, 1 fewer jump. Right, guys, stay focused. 1 fewer jump. So just like arithmetic, in order to get the nth term, we need the first term, but instead of arithmetic where we're adding, we are multiplying. We're geometric now. And we're multiplying multiple times, which means I need an exponent. And that exponent will signify 1 fewer jump to get from the 1st to the 10th to the 100th to the 1000th, whatever I need to do. Could this be a good formula to memorize? Yes. But can we maybe understand it too? I hope so. So you guys ready to practice it? You guys can start writing. The next example, find the 12th term of him. Find the 12th term of him. Yes, how do we signify 12th term? What's the notation as you write it? A sub 12. Does that make sense? Which A, which term? The 12th one, please. Wait a minute, he's getting smaller.
1/4.
Exactly. We can find the common ratio by saying, what's 24 over 96? I wonder if that's the same thing as 6 over 24. We can say, what was multiplied to go from here to here? And the answer would be, both of those reduced to 1/4. So you can think divide by 4. That's not bad. But we need to think about multiplying by 1/4. You can think divide by 4 is the pattern, and you're right. So translate that into, then the common ratio must be 1/4. Does and hopefully you guys are plugging and chugging. I'm gonna freeze the screen, I'm gonna plug and chug and we'll compare. Using the formula from the page before. He's not a pretty one. You plug in and chug him. I know he's not nice, but he's possible. Is he a nasty one? So remember, don't do 96 times 1/4 first. PEMDAS, 1/4 to the 11th first. Why 11? Because it's one less, one fewer jump, right? Than the term that we're going to. Raise 1/4 to the 11th and then times 96. You guys agree? Yeah. Did you try changing him to a fraction to make him pretty? It didn't work anyway, it's okay. So question. Let's take away this awkward wording that I see down below because it shouldn't be find the indicated sum term. That's kind of two things at once. Find the indicated term. Forget the sum. We're not doing series yet. I know it's awkward, I apologize. Find the indicated term of the sequence. Wait a minute, what? What term do they want?
The first
Yeah. Well, that's weird. Don't you always get the first term?
one.
Not this time. How do we use all the ideas we've seen in order to use the second term and the fifth term to find the first term?
The common numerator.
Yeah, we do see a common numerator. Maybe the 3 stays a 3 no matter what. Yes, the difference grammatically speaking, but not the difference mathematically speaking. I don't want to think subtraction. What do I want to think?
Jumping.
Jumping with geometric is an addition. Multiplication. There we go. Now, one way of visualizing that I use, I don't know, I'm more of a visual person. I kind of like doing this and saying, hey, there's the second term, which is 3. Third term, I don't know. Fourth term, I don't know. Fifth term, I do know. I like kind of thinking in my head as far as the placement in the sequence. Because that kind of helps me think about how many jumps of the common ratio, because it said geometric. How many jumps of the common ratio should have been between those two. Does that make sense, guys? So I can say 3 times how many r's? R to the power of 3. Times r, times r, times r, because each of these indicates a multiplication of the common ratio. Has to equal what?
3 over 6.
So it's kind of making your own formula and saying, hey, I know where to start. I know how many jumps, and I know it's by a common ratio because it says geometric. How would I solve? Multiple ways. But one way is you can divide by 3, the 3's cancel. You can cube root both sides. And a cubed root of 64 ends up being 4, and so then the common ratio is 1 over 4. But that's not the final answer. But can I use it?
Yes.
Yes.
Go back a step.
Now, we can do this actually multiple ways, meaning we could say something like, hey, I know what the second term is. The second term is 3. I don't know what the first term is, but I know the common ratio is 1/4, and there was one jump of that in between. You could set up a little formula with the a sub n term and say, well, I know what a sub n is when n is 2. So you could say 2. The second term, a sub 2 equals 3 equals the first term times 1/4 to the power of 2 minus 1. And you could solve that. Another way is to think, how could I go backwards?
Divide.
Instead of multiplying by r, I could divide by r. So instead of multiplying 1/4, I could multiply by the reciprocal, which would be
12. Or 4.
4. Or you could just ask yourself, who must have been multiplied by 1/4 to get 3? 12. So whether you solve a little baby equation, or whether you think of just going backwards and who must have been multiplied by 1/4, either one should get you to the final answer, multiplying by 12 on that side, multiplying by 12 on this side, of the first term being 12. One of them is much more logical, and that's this way up here. Who divided by 4 would have gotten 3? 12, of course. For some of us, that logical is a big jump to make. The other way is plugging in that a sub n formula, solving, and then saying, oh, the first term must have been 12. Alright, you guys ready? Now, let's go to series. How do we know they're series? Because there's a big ol' S and there's a big ol' sigma. Once again, probably an important formula, huh? Maybe, sorta, kinda? Sorta, kinda, maybe? It's time to go to series. It's time to go to series. In the olden days, if it was a series of 2, 3, 4 terms, we would find the 2, 3, 4 terms and add them all up. After you write this formula, look at that example. It says add 12 terms together. Ugh. Who wants to do that? No. Example could say from 1 to 12, it could say from 1 to 50, it could say from 1 to infinity. This one just says from 1 to 12. Geometric series can show up different ways in the sigma notation or in this formula. But almost always it does look similar to some sort of number times some sort of ratio raised to a power. It can show up different ways. But always, always, always in a geometric series, the index will show up in the power of a number. But if it's a little hard for you to see, or if it doesn't match this precisely, this middle part is not really the point. I'm going to put him in parentheses. He's good and all, but he's not really the point. The point is the nth partial sum of a geometric series can be solved using this formula. A little bit more complicated than Gauss's way for finding the sums, partial sums of arithmetic series. If worst comes to worst, that part in parentheses, you can disregard entirely if you would like, and you just would then have to look at every problem and say, hey, who are you? Well, it's kind of hard sometimes to tell who he is based on the sigma or the summation formula and the sigma notation, but if you start plugging in stuff like, hey, what's a sub 1? Well, plugging in 1. 1 minus 1 would be 0. Anything to the 0 would be 1. 4 times 1 is 4. So I could say a sub 1 is 4 plus. A sub 2, I would plug in instead of I is 1, I plug in 2. 2 minus 1 is 1. 1 times 0.3 is 0.3. 4 times 0.3, ew. Never mind. 0.3 to the 1 is 3/10. 4 times 3/10 would be 12/10, which would be 6/5. But 6/5 might make it a little bit hard to see the pattern, so we'll just keep 12/10 for right now. If we were to go again, we would need to plug in, instead of 2, we would plug in 3. 3 minus 1 is 2. 3/10 squared would be 9/100. 9/100 times 4 would be 36/100. And yes, once again, these do reduce. I'm just trying to show you the idea of what we're doing. If you weren't able to see it was geometric in the sigma, you can see it's geometric based on, hey, aren't we multiplying by 3/10 every time? So sometimes if the sigma, if the way this formula appears is confusing, you can always expand or start to expand the sequence, I apologize, the series, and say, hey, can I find a pattern? Well, I changed it to 3 because when I was down here, I plugged in 1 first, and so I changed to a 1 and thought about it, and it was 4. Then I plugged in 2, and you just happened to catch me when I plugged in. So once again, you could reduce, but it's sometimes hard to see the pattern when you reduce. Every times 3/10 times 3/10. So, question, is this a geometric series? And the answer is yes. What's my a sub 1?
4.
What's my r? 3/10. And once again, yes, you can compare these two. The little double-sided arrow I just drew. You can compare those two, and you could pull out a sub 1 and r in this example from the formula. But I'm trying to say sometimes they show up in ways other than that formula that I crossed out above. So I'm just trying to show you how to find the geometric information that you need every time. But question, kiddos, what's the point of this problem? Without our calculator, what are we trying to, or at least without needing to use the sigma notation in our calculator, what are we trying to be able to do or solve for when it says stop at 12? Yep, the sum of the first 12 terms, which means the 12th partial sum. So I'm trying to find from that problem S sub 12. And we have a formula, right?
Yeah,
Look up to the top. What's a sub 1? What's my r? What am I raising that r to the power of? Ew. All over 1 minus r, which is 3/10. Now I said without using the matrix, sorry, not the matrix, the sigma notation in your calculator. There is sigma notation in your calculator, struggle. And we already looked at that before the SAT, wasn't it like last Friday or something? You guys remember where the sigma notation was? The Greek letter? Math, go up, and it should be the second from the bottom, third from the bottom. If you have a nice newer calculator, if you have the yellow button, it will not and nor can it ever show you this, sadly. In your calculator, you could say from 1 to 12, and you could put in the little thingamabob 4 times 0.3 to the power of, and you can use whatever variable you put in for your index. I'm using x because who wants to go find the I? Not me. And you can get 5.714282677, or you could plug in this nifty-difty formula that we just did. 1 minus 3 over 10 to the power of 12, all over 1 minus 3 over 10. And make sure you have your 4 on the outside, and either way you cut it, whether you plug this guy in your calculator using the math button, or whether you plug this guy into your calculator using the formula, maybe your cool alpha fraction you do, either way you end up with a decimal that does not come down to a nice pretty fraction, and that's okay. 5.714. You guys agree? Double check. Double check parentheses, double check numerators, denominators. Not bad, right? Now, would you have to do this one mental math? And the answer is no. Look at that. He's to the 12th. That's disgusting. But here's something crazy. Basically one of the last questions we'll talk about today. Ooh. I have random extra examples. One of them is not written down, and for sake of time, let's just kind of skip them and see if you guys do all right with that type of homework problem when you get to it. How would you do number 72 if they give you the series but they don't give you the notation? What does it say to do? Write the sum. What's that Greek letter called? Sigma. You guys remember how to make it?
Yeah.
Ready? Do like a curly Q, over, up, then top it. I do a little curly Q.
Oh, I just do a sideways kind of thing. I didn't like it.
I like my kind of like envision a rectangle.
Doesn't mine look cool though?
Yours looks cool,
You
but
can do it fast.
it looks funny.
You just swoop it over, up, and then
I just like go like, I just put it like that.
okay, you do you. Anyway, we need to figure out the bottom, we need to figure out the top, we need to figure out our formula. Struggle. What do we know?
First one.
Yeah, we usually start at 1. That sounds good. We know a sub 1. What's going on here? We're subtracting 8 and then subtracting. Oh, that's not going to work. It's not arithmetic. Can we try geometric? What's 24 over 32? Remember, I have to divide? That's 3/4, yeah?
Yeah.
8 into 24, 8 into 32. What's 18 over 24? Is that the same? Oh my goodness, he's geometric. Alright, so what's my R? Do you see how sometimes R is hard to find? You kind of have to like take a ratio to figure it out. Ooh, that's why it's called a ratio. Okay. Wait. Can't that formula on the page before, that little sigma that we crossed off, help us in this one?
Yeah.
Okay. It says, take a sub 1, 32. Multiply him by the common ratio, 3/4. And we're not done yet, because I think that formula says, take a sub 1, exactly, multiply him by r raised to the power of I minus 1. So, we still need to put a little I minus 1. But the struggle is, kiddos, we still haven't been able to fill in
Where do we stop?
where to stop. What's their one clue?
The,
The end point?
whatever that point is.
Ugh.
Not really the end.
We don't know who, well, he's like the last term, right?
Yeah.
He's the partial sum point.
But he's not really, I mean, he's a part of the partial sum, but isn't he just a term in the sequence? Oh, come on, ding, 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 anybody? Term in the sequence? Term in the sequence, isn't he an a sub n? Which a sub n? I don't know. Let's go figure out which a sub n. How? Use the formula. What's the a sub n formula for a geometric sequence? A sub 1, which is 32, times r, which is 3/4 to the power of? Ooh.
I minus 1.
How do we solve for an n?
Logarithms?
Yep, sounds good, but first let's divide by 32.
Yeah.
Then let's go ahead and take ln of, I don't know, this messy guy I'm not doing yet to avoid error. We can take ln of this side. What happens to ln's with powers? What can we do with those little guys?
They can't.
It doesn't
Take him down. Take him down. Take him down.
Take him down, take him down.
Yeah, Nicole.
One is in
Remember with ln's we take him down?
Yeah.
Oh, we're so close. Kiddos, guess what? We're not close enough to have this homework due tomorrow, but oh man, you better get a start on it. Get a start on it, it's due on Friday though. Bye guys, happy Wednesday. Thanks for doing some high day leftovers. I'll collect those bonuses then.